Okay, guys, we were ready for 4, and they give us the radical function, the square root of x. So, let's work through this here. Use the difference quotient to find the slope of the curve at x equals 9. Now, when we talk slope of the curve, what are we talking here? What are they fancily trying to say?
The tangent line.
Tangent line. So we need to find the derivative, yes? So this is using our limit form. I am going to be squeezing to get this in, but the limit as h approaches 0. Now, f of x plus h. What's f of x plus h?
You have to plug in the 9.
So let's see. You don't have to. There's 2 different ways you can do this. Is you can plug in the 9 now, or you can wait till later. In my notes, I waited till later. And the only advantage there is you get kind of a formula for the derivative you can use. I don't think we're going to have to use it, but yeah, I don't know, do we want to plug the 9 in?
I don't know. I feel like that's how we're formulating it.
And here's the deal. Okay, so you have an option. You can go ahead and plug in 9 right now. Or you can wait, get your formula for f prime of x, and plug in 9 after you have your formula. Now, if you were having to do multiple derivatives, like multiple different x values, then I would just want to get a formula and plug it in at the end. Does that make sense?
Yeah.
But, okay, so yeah, if we use the fact that x is 9, so then instead of f of x plus h, it's going to be f of 9 plus h, which is going to be what? Square root of 9 plus h minus f of x, except instead of x we're using 9, so minus the square root of 9 all over h. Now, square root of 9, at some point you could call that 3. But we have a radical up top, yes? That radical is not okay. In order to, or radical minus radical, what are we going to do here? Yeah, we're going to multiply by conjugate, square root of 9 plus h plus, can I just say 3?
Yeah.
Over square root of 9 plus h plus 3. Okay, continue. The limit as h approaches 0. On top, square root of 9 plus h times square root of 9 plus h is 9 plus h. Outsides and insides cancel. Minus 3 times 3. Minus 9 over h times the square root of 9 plus h plus 3. Are we good there? Clean up. 9 minus 9 cancels. How fancy can I get? Can I go ahead and cancel the h's? And so if I go ahead and cancel the h's, I'm going to be at the limit as h approaches 0 of 1 over the square root of 9 plus h plus 3. Yep. I can't do anything else to simplify, so we should be ready to plug it in. When we plug it in, and this is what, well, yeah, so when we plug it in, we're going to have, I'm going to bring it over here, 1 over square root of 9 plus 0 plus 3, so we end up with 1/6. Okay, this was the slope of the curve at 9, so this is m. It is also f prime of 9, and it is 1/6. Okay, so f prime meaning the derivative. This is the derivative at 9. Okay. B should be easy then. Write the equation for the linear approximation of f near x equals 9. Linear approximation. Fancy way of saying tangent line. Okay? So what do we know? Right, we already know that the slope we're going to use is 1/6. What else do we need to know?
X is 9.
What?
X is 9.
X is 9, and if x is 9, then we need the y value, which is 3. So the ordered pair 9, 3, if you will. Now, if you recall the way she was setting up the equations here, point slope, but kind of the alternate form of point slope, right? Instead of y minus y1, just do y equals m times x minus x1, which is 9, and then plus your y value, so plus 3. Okay, now C. Ask us to use the equation that we just wrote in part B to estimate the value of the square root of 9.1. Notice it says do not use a calculator, show your work. But I'll tell you guys, the do not use a calculator, it's threatening, but yet the way this equation is set up, it's doable. Okay, so y equals, so when we say square root of 9.1, what are we putting in for x? Oh, I guess I don't have y equals, I have f of 9.1. We're putting 9.1 in. So f of 9.1. And it's because our original equation was square root of x, we're trying to find square root of 9.1. So our x is 9.1. So what do we have here? 1/6 times 9.1 minus 9 plus 3. Well, 9.1 minus 9 is 0.1, yes? Now, I'm not supposed to pick up my calculator. I have the fraction 1/6 times the decimal 0.1, or properly read, what is 0.1? It is 1/10. So I would turn this into 1/6 times 1/10 plus 3. And 1/6 times 1/10 is 1/60th plus 3. So my brain goes 3 and 1/60th. Now, we don't use mixed numbers at this level of math. So make it improper. Or, oh, I have a decimal. How do I have a decimal here?
Did you do 1/6?
No. I have 3 and 1/60th actually, and then I just wrote the decimal. So I don't know if it was something I was claiming you might know. Because I don't know 1/60th, but I have it. This part would not, this would be with a calculator for me, but 3.0166 is what it is, you know. That's the decimal. Now, here's the deal. 3 and 1/60th. I think Aiden, someone was getting the improper fraction. Okay, that's doable too, right? Whatever you need to do there. Okay. Graph the function and its tangent line at x equals 9. So what's the original function? Y equals square root of x. So I can make an xy chart, or we can just think through this. 0, 0. What else is points? If you put 1 in, the square root of 1 is 1. So the square root of 0 is 0, square root of 1 is 1. What's the next one I would use?
2.
What's the square root of 2?
4. 4. Square root of 4 is 2.
So the square root of 4 is 2, so the ordered pair 4, 2. What can I use next? 9. The square root of 9 is 3. We can go one more based on the way this graph is set up.
16.
The square root of 16 is 4, yes? So there is your graph. It's half of a sideways parabola. You can also just reverse in a parabola 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. It's just those pairs reversed. And it also wanted us to graph its tangent line, right? So tangent line at, what was the point? At x equals 9. So at x equals 9 is right there. What's the tangent line going to do? It's going to be something right on top, yes? My graph isn't drawn great, so it's not the best, but something right on top there. Okay. Now, based on this information, explain whether your answer to C, so that f of 9.1, is an overestimate or an underestimate for the actual value of the square root of 9.1. Justify your answer by reference to the behavior of the graph of f of x equals square root of x. So 9.1, we would use the tangent line, yes? So you've got here this point of 9.3 that we know, and then we came up with the point of 9.1, that 3.011 or 166, right? And I know that's not exactly right, but we talked about this previously one time. Overestimate or underestimate?
Okay.
Why is it an overestimate?
That's above the graph.
Right, because your tangent line is lying on top of the graph, right? And when you talk about the fact that the graph is curved down, I use that word concave down, right? So because the graph is concave down, it's an over approximation. And that's because the tangent line lies above the curve. Okay? So overestimate, because graph is concave down, and tangent line lies above the curve. Okay. Maybe the reason I have this filled in on C is because of F. F says find the true value of square root of 9.1. Well, that's a calculator thing, yes? That's a calculator thing. I have the square root of 9.1 written down as 3.01662 ... Well, I probably didn't really express this up here, but that 3.0166, it was actually 66, the 6 was repeating. So if that's the case, or wait, maybe it was exact. Double. Yeah, okay. Okay. Now, this worked. We found this was all based on finding at 9, right? and we are trying to then estimate 9.1. G asks, would your linear approximation formula be an accurate tool to estimate the square root of 25? Our linear approximation tool right here, what values did we use to help find that? We used the values based on x equals 9. Is 25 close to 9? No, not really, right? Okay, so this linear approximation tool that we just came up with here, this works well for values around 9, values in the neighborhood of 9. Something like 25? No. You need something closer to 25 to be able to estimate something like that. Okay, it's like, for instance, if we want the square root of 25.1, you need to find a linear approximation, or in other words, the tangent line for square root of 25. Okay, so this only works for values very close. So, I have no square root of 25 is too far away from the point of tangency, which was 9, and it's outside the local neighborhood. So however you want to write that, no. Root of 25 is too far from the point of tangency. And our point of tangency in this case was x equals, whoops. Gosh dang it. I'm also going to say outside the local neighborhood. Okay. Yep. Thank you much. Okay. Let's start with me about a moment. Okay, moving on. Oh my gosh, that one page took forever. But it was good stuff to go through. If you know, it was stuff we need to talk about. So we'll do a couple of these. We're not going to do all of these on this page because okay, example 5. Use the graph, the continuous function, to complete the table. We know the derivative of function represents the slope of the tangent line. At that point, we're being asked to estimate the value of g prime of x for each x value in the table by drawing a tangent line through the given point of tangency. Then estimate the derivative, or the slope, at the point. Find the y-coordinate of the point of tangency and use the point-slope form of an equation to write the equation of the tangent line at the point x equals a for each x value. Now, tangent line approximation of f at a. This looks funky, guys, but this is really what, think with me for a moment. F of x, that's a fancy way to say y, right? F of a, that is y evaluated at a, so think of this as like your y1 plus f prime of a is your slope times x minus a, well, that's your x1 value. What is that really? That's just our point slope form. But instead of putting, what have we been doing? We've been putting the y1 at the back. This is the y1 at the front. Do you see it? Okay, I knew I needed to make sure you saw it before we proceed, because otherwise you're like, wait, another new thing? No, it's just them writing it fancy. Okay, so, okay, x equals a. So our first value is at -3. Well, what do we notice at -3? That's point A, isn't it? Okay, so if we're going to draw an approximate tangent line, nope. You guys draw your tangent line. Oh, that's kind of my tangent line. I don't even know if I'm going to match up with what I expect the estimate to be. Okay. Ruler time.
I can't get it straight.
I wish I could use a ruler on the BenQ, let me tell you, because I can't either. Enjoy your rulers, because I want a ruler. Okay. Estimate your derivative when you're ready. Obviously, we're using point A. My line is not particularly straight.
-7.
Yeah. Looks like mine is between -6 and -7. My answer key has -6. If we're at -7, are we in the ballpark? Are you in the ballpark? Okay. So either of those, you know. How about if I say -6 or -7? Because as I said, mine's kind of in the ballpark. Mine almost looks like -6.5. Because if I go up 6 and left 1, or up 7 and left 1, it's kind of right in that ballpark. Okay. What is our point of tangency? In other words, what point was this? It was point A, which is what ordered pair?
-3.
3 left, 3 down. Function behavior. Increasing, decreasing, or constant. What is the function doing at this point, at point A?
Decreasing.
It is decreasing, yes? And that's indicated because we have a negative derivative, yes? Negative slope. So this is decreasing. So, can you write an equation of the tangent line here? Y equals?
-7.
-3.
Well, okay. Which one are we doing, right? I guess, and here's, I don't care. And actually, I don't even have to. So, let's see. Because I actually have both on my notes. So, if we say y equals, if I go with the -7, okay, she's starting with slope. So, -7, -6, whichever. And then x, parentheses, x, what?
+3.
Minus -3, so +3, and then outside you have a -3.
I thought
That's what we're used to doing, yes? Or if we, and I still have it in terms of y and x, yeah. The other idea here is if you put the -3 out front, which is that what you tried to do, Aiden? So -3 minus the 6 times x plus 3.
does it matter which one you do?
And here's what I'm going to say. Know their equivalency, right? If Caitlin writes one and Aiden writes the other, don't look at each other and say you're wrong. Understand that we have the same thing. Okay? Let's do 2 more and then I'll be honest. I'm going to skip off of, or 1 more, and then I'm going to skip off of this page. Let's go ahead and do the next one. Why do I want to do the next one?
Oh. Isn't it 0?
Yeah, because if you're drawing the, gosh, I can't even draw a horizontal line, guys. Yeesh. But at -2, that's point B, which is a minimum, yes? It's a minimum. Your tangent line is horizontal. So what's the derivative estimate? 0, right? In other words, because we're talking slope here, aren't we, when we talk derivative estimate? The point of tangency? -2, -6, it looks like. The choices are increasing, decreasing, constant.
Constant.
constant, right? Because that's flat at that point. You're not increasing or decreasing, because my other option would be, I would say, a minimum. That's what comes to my brain if I'm not looking at what my, choices are. Now, what's the equation here?
X plus 2. Wait, wouldn't it just be
Or would it just be y equals
negative?
x?
Because the slope of 0 means 0 times the x minus whatever is gone, so it's just the y value, right?
Yeah.
The rest of these would be the same old, yes? I don't feel like that's a necessity for us to go through. I didn't show you an increasing, but is it that different? No. The notes, this morning I put the answer key for homework and the notes on Schoology, so if you want to look at them, you can, right? I'm still not going to make it through all these notes, but I can at least make it a little farther, right? Okay. Okay. As we look at this next spot, when you plot the motion of an object as velocity versus time, okay? Sorry, I'm checking something real quick. Yep, that's what I thought. I've spent 2 days on this in the past. Okay, when you plot the motion of an object as velocity versus time, these are referred to as slope functions, or f-prime graphs, okay? In the study of calculus and physics, these graphs represent the rate of change of the original function. By analyzing these graphs, you can find where changes are occurring slowly or quickly by observing the rates of change or slopes of the tangent lines at specific moments in time. So this is where we start talking about being able to draw a derivative graph, okay? So, consider the function shown at the right. Notice the curve at the first point, x equals 1/2. The slope of the curve here appears to be about 1. Then at x equals 4, the slope has decreased to about 1/3. Can you analyze and sketch the slope graph on the grid below? Okay, so, and I guess I called it a derivative graph. It's the graph of the first derivative here, right? So we're no longer graphing x and y, we're graphing x and y prime. Okay, so, for instance, right here, that is the x value 1/2, right? And it was mentioned that the slope there appears to be about what? And it appears to be about 1/2. So we can, or 1, excuse me. So we can go to 1/2 and up to 1, and we can put a point there. And that's based on that information right there. We also know when x is 4, I don't care that the y value is 2.5. What's this slope? And they're estimating the slope is approximately 1/3. Okay, so rise 1, run 3. So then that becomes the ordered pair 4, 1/3 when you're doing x and then f prime. So if we go over 4, up 1/3. Can we pick out some other points? Okay, and that's, we can. You can pick out as many points as you want. I'm trying to think, do I have any other points? I don't know. They have a ton of other points, but okay, let's look before this point here. So right here, this is about at 1/2, right? What do we know about those slopes before? So like over here at say 1/4 or 1/8 or whatever. What do we know about the slope over here? If I were to draw a slope graph, say right here, and I'm not going to leave this on here, but what's going to happen? It's going to be even steeper. Or when we talk about steeper, we're talking about a larger graph, yeah, or larger slope, yes? So as you think about that, then what that's saying over here is, okay, so say at 1/8, 1/4, whatever, those numbers are going to be up higher. Does that make sense? Because we're going to have higher slopes. I mean, you know, right there, I don't know what that slope is, but it's going to be higher. So these numbers are going to be higher, and those are just kind of, you know, random dots I'm trying to get you to think of. What happens as we go farther out here? You know, like if I pick a slope over here, it's becoming closer to 0, yes? So if it's becoming closer to 0, where are these values going? They're going down, yes? Okay. A square root graph. Officially, what's it doing? It keeps going on and on forever. It doesn't end up ever going down, does it? It keeps going gradually high. So is it ever going to hit 0 or go below 0? No. So what we're looking, do you see the shape that I'm kind of making here? What we're looking at for this slope graph is kind of like what you see on the reciprocal function or whatever, where it's just a curve that follows those lines, or follows out on the x-axis and y-axis. Okay, so that's how kind of a slope graph works, is you kind of find some key points to kind of give you an idea of where you're going with it, and then you fill in the pieces farther. I want to go down on number 7 here and compare some of the pieces. I think that will help if we kind of compare and pull them together. Now, on the left, we have the original function. On the right, we have the slope graph, right? So we have the original function, we have the slope graph. The f prime graph, so the slope graph, gives us insight into the behavior of the original function. For example, at x equals 1, the slope appears to be almost -2. So they're saying right here the slope appears to be almost -2. So notice, where is that down here? It's over there, because that's where the slope is. Therefore, on the y prime graph, the value of x equals 1 is almost -2. Several other relationships. So right there, what is this graph doing here? This graph is decreasing. It's decreasing from where to where? If we just look at this piece right here, on the original graph, it is decreasing, yes? Any slope line, any slope you draw here is going to be what? It's going to be decreasing, it's going to be negative. What do you notice over here on the slope graph between approximately -1 and 4? It's negative, yes? So a decreasing graph means a negative piece on the slope graph. Okay? A max and a min over here are zeros over there. Like, these are all connections that we can make. Also, think about it. What is the slope here at this max and the min? 0. What is this value? 0. Okay, so things like that are good to notice. I'm trying to think what else. Let's go to the other page real quick. I think I'm going to go to the other page because they ask us, if you open your book fully, they ask us questions about this, if I recall. Because it said, yeah, 7 continued. So when the graph of a function is rising, we will say the function increases. And when the graph is falling, we say the graph decreases. It is customary to read a graph in the same way we read a book from left to right. Now, look at this one. Starting at the left on the original graph, state the intervals of x where the graph rises. What do you notice about the slope of the curve on these intervals? So when the graph rises, what are we saying? Rises, increases. Okay, so where the graph increases, whoops, wrong way. Where are we increasing? We're increasing here, yes. And where else are we increasing? Over here. So I had that increasing like negative infinity to about what, -1 and 4 to infinity. I had 4.2. Really? I'm sure that was not my value. But f of x increases negative infinity to -1. And I'm just going to write it as 4 to infinity. It's close enough. When it's increasing, the slope is what? Slope is positive, yes? Increasing graph, slope is positive. Notice in those same intervals on the other graph, where is the graph? It's above the x-axis, right? From negative infinity to -1, it's up here. It's a positive slope. Same thing, 4 to infinity. Over here, it's positive slope. Okay, B. Starting at the left, state the intervals of x where the graph falls. What do you notice about the slope on these? Well, when the graph falls, what are we talking about? That is decreasing. Where's it going to decrease? -1 to 4. In between where it was increasing. And what did we already talk about? The slope there is negative. Okay? I'm trying to shortcut here. I think I've already covered most of this now that I look. At what values on the x on the graph does the function appear to have a max or a min? What is the slope at these points? What characteristic on the slope graph occurs on f prime? So, let's see. F has a max. And they just really are asking about the x value, right? What values of x? So where was there a max? That was over at x equals -1. And then it's going to have a min over at x equals 4, right? Are you visualizing the graph? You have the graph in front of you. Okay. And what did we already talk about? What did we notice on this? Dang it, wrong way. Slope graph? Those are what? Zeros, yes? So zeros on the slope graph always match up with maxes and mins there. Okay. Slope is 0 at these points. Okay. And now I didn't talk about this one, so we'll take this back. Now, on why does the derivative graph, the slope graph, have a minimum near 1.5? Can you explain what is occurring on the original graph? So, 1.5, yes? Right here there is a minimum. What does that connect with over here? 1.5 is about there. I think we've talked about those types of points. Yeah, it's called a point of inflection officially. Okay, because what's changing? We change from being curved down to being curved up. So your concavity, there's the official word. Your concavity is changing, and this is, I always call them inflection points, but you usually see them as POIs. POI standing for point of inflection. Okay, but that right there is the connection. So on F, graph changes from concave, what was it, down first? Yeah. Concave down to concave up at x equals 1.5. Okay? Okay. Now, the next page is the important page. So if we don't get to that back page, I'm not sure I'm going to care as much if we don't get to that back page. But now, what we're getting ready to do is we're getting ready to practice sketching our own graphs here. Okay? Some thoughts here. Describe how the slope changes from left to right along the curve. Notice intervals where the slope is positive, negative, 0. Like, these are things we have to notice to draw our slope curve. Write down the changes from left to right on number line. Notice where the x-intercepts occur. Pay attention where the function is above, positive, or below, negative. Okay. With this in mind, here's g of x. Over here is going to be our slope curve. So it's all about the slope here. Okay. What is the graph doing over here? First thing this graph is doing is what? What would you call that? That is where the graph is decreasing. Okay. Now, and we're decreasing to what point? Okay. I'm only going to care about the x values right now. So we're decreasing up until negative 2, yes? Which, if you're decreasing up until negative 2, well, we'll come back and talk about that in a moment. Okay. So what's the graph do next? It goes up, yes? So now, as it goes up, it is what? We're increasing, and how far are we going to increase? Okay. She says we're increasing until 3. 3-ish, yep. And then what happens after 3? Again, we are decreasing. Are you with me so far? Okay. Now, in terms of slope, what does that mean? So like right there, those were all G. A decreasing graph means my slope is going to be what when I get over here? No. If my graph is decreasing, well, in other words, what is the slope over here? It is negative. And actually, maybe I phrased that wrong, I guess. But the slope is going to be, it's going to be negative. Okay. From negative 2 to 3, it was increasing, which means it is positive slope. After 3, it is decreasing, so it is a negative slope. So what that tells me when I get over here, because that's what I'm trying to get you guys to see, is that tells me when I get over here, negative 2 and 3, yes? That tells me when I get over here that how do I want to do this? My graph has to be negative, then positive, then negative. Okay? Now, I'm trying to think, what other things do I need to mention? right here and right here. What are those slopes? 0, yes? Because we have here a min, and here we have a max. And so with that in mind, my slope is going to be 0 at those points. Okay. And what do I mean if we're talking a 0? What's that going to mean when we get over here? That's an x-intercept, isn't it? So I know if we want to go ahead and put them on, I'm going to have an x-intercept at -2 and at 3. Okay. Thoughts on a point of inflection? It's totally a random, it's hard, it's hard to tell an exact. I don't know, where does it change? Almost 1, yes? I have 0.8 written down. It's totally but it's somewhere before 1, yes? Before 1, I wouldn't be against 0.5. But, 0.8, 0.5, something along there. So that right there is our point of inflection. Now, what's that going to translate into over here? Okay, it's got to be a min or a max, and it's going to end up being, because we're going to be what? Negative, positive, negative, so it's going to be negative, positive, negative. That's going to end up being your max, right? So somewhere above 0.8. Now, officially, I don't know, thoughts? What's the slope at that point? The slope at 0.8, maybe something around 4-ish, just under. I have something just under. So if you think here at 0.8, it's just under 4, you kind of see what I'm going to be drawing? Okay? That we have to be negative over here, positive over here, or excuse me, negative and negative, positive in the middle. That's going to be your max. And so the graph we're going to draw, it doesn't have to be very precise, folks. Helps if I can hit the dots, though. But it's just going to essentially be like an upside down parabola. Okay? Trying to think what other. Oh, what other pieces do I need to make? There was something else I wanted to. Oh, I guess here we talked about this. It was our point of inflection. Before the point of inflection over here, it was concave up. Notice this is increasing. Over here, concave down. Notice that is decreasing. So that comes from your original G, that this was, I'm going to use CU for concave up, CD for concave down. It takes a little skill. It takes a lot of practice, okay? It's not my strongest thing either, but what you're going to need to be able to start being able to do is, I don't know, maybe you have to draw some in homework, not necessarily, but it's more going to be the matching skill. Yeah, that page 111 of homework is matching. You're taking the 8 graphs at the top and matching them with the 8 derivative graphs from the bottom. So you're trying to figure out some connections, and that will be something that we may have to talk about. Okay? real quick, I guess they gave us some directions here and I didn't do, mark the number of line above. Yeah, I guess we were supposed to be following the directions, but what does extrema mean? Mins and maxes, yes? I just brought that up in pre-calc today because we learned extrema. Extrema, fancy word of saying mins and maxes, right? We learned that last year in pre-calc. Okay. Now, the page I haven't gotten to. Let's see. Yeah, I don't see a ton that has to do with it, but on this last page, AP, they love graphs, they love tables. Oh my gosh, they love tables. Okay, so tables are a normal thing. We've seen it's possible to estimate the numerical value of a derivative at a single point by finding the slope of the secant line. Slope of the secant line is how you've been doing slopes since Algebra 1, right? Let's explore how this can be done with the table. So they give us a table of values there, and it says find the derivative for each x value. Describe the behavior of the function, explain your reasoning. So what we're looking at here, f of negative 2. Okay, so here's negative 2. Derivative. Well, what's going to be the easiest way to find the derivative there? If we're going to do slope of a secant line, it has to be the line that goes through points on either side of it. So it'd be the idea to do the derivative to use the points, basically the -4, -6, and the point -1, 4. So 2 points close to it, but yet we're not using those points. So if we do our slope there, which slope, or I'm going to call it f prime of 2, the derivative at 2. What am I doing? I just said 6 minus 4, -4 minus -1, so -2/3.
It's -6.
Okay. I'm like, why does that not agree? Man. That's what I was like, I looked down at my notes just then, and yeah, -10 over -3, which, what is a negative divided by a negative?
Positive.
Positive. Don't leave me negatives over negatives. Okay. Because it's a positive slope, I know my graph will be increasing, and your justification of that is that the derivative is greater than 0. So, okay. Yeah, we didn't get through that page, but
Don't do our homework.
yeah, no. Do the homework. Do the homework.
Gee.
Answer key is posted. The notes key is posted. Do the best with what you can. We'll talk tomorrow, right?